Look up at the night sky, really look at it, and tell me what you see. Stars, yes, countless pinpricks of light scattered like diamond dust across the velvet darkness. But between them, hidden in the shadows, lie the universe's greatest artists, nebulae and star clusters, the silent weavers of cosmic creation. These aren't just pretty clouds of gas or random gatherings of stars. They're the birthplaces of suns, the graveyards of giants, and the engines that shape galaxies themselves. Think about that for a moment. Every star you've ever seen, including our own sun, began its life in a place like this, a swirling, chaotic cradle of dust and light. And right now, somewhere out there in the infinite black, new stars are being born in these celestial nurseries, while others meet their fiery end, scattering the ingredients for future worlds across the cosmos. What's even more astonishing is how these structures hold the answers to questions we've asked for millennia. How did we get here? What are we made of? Where do the elements that compose our very bodies come from? The story of nebulae and star clusters isn't just about distant clouds of gas, it's about us. The iron in your blood, the calcium in your bones, even the oxygen you're breathing right now. All of it was forged in the hearts of stars and scattered across space by the very forces we're about to explore. This isn't just astronomy, it's a cosmic genealogy, tracing our origins back to the fiery furnaces of creation. So let's begin this journey together through the violent explosions of dying stars, the serene beauty of stellar nurseries, and the unimaginable forces that twist gas and dust into galaxies. We'll uncover how these celestial phenomena don't just light up the night sky but dictate the fate of the universe itself. By the time we're done, you'll never look at the stars the same way again. Because once you understand how nebulae and star clusters shape existence, you'll realize something extraordinary. We're not just observers of the cosmos. We're made from it. To grasp the true scale of these cosmic masterpieces, picture this. The average nebula stretches across light years of space, so vast that even at the speed of light, it would take centuries to cross one. These colossal clouds aren't just floating passively, they're dynamic, ever-changing tapestries where gravity and radiation wage an endless tug of war. Take the Orion Nebula, for example, a stellar nursery just 1,500 light-years away. Inside its glowing folds, newborn stars ignite like fireworks, their fierce ultraviolet light sculpting the surrounding gas into towering pillars and rippling waves. It's a celestial dance of creation, where every swirl and knot holds the potential to birth a new sun. But nebulae aren't just cradles, they're also echoes of stellar endings. When a massive star exhausts its fuel, it doesn't fade quietly. It explodes in a supernova, blasting its guts across space in a kaleidoscope of color and energy. The Crab Nebula, the remnant of a star witnessed exploding in the year 1054, still pulses with the energy of that cataclysm, its filaments expanding outward at millions of miles per hour. These death throes are anything but futile. In scattering heavy elements like iron, gold, and uranium into the void, they seed the cosmos with the raw materials for planets and life. Star clusters, meanwhile, tell a different story. Imagine a family of stars, thousands or even millions strong, all born from the same primordial gas cloud. Open clusters, like the Pleiades, are loose sibling groups that gradually drift apart over eons. Globular clusters, though, are ancient relics, dense spheres of stars orbiting galaxies like bees around a hive, some nearly as old as the universe itself. Their tightly packed stars are a time capsule, preserving clues about the early cosmos. By studying their composition, astronomers can trace how galaxies assembled and evolved over billions of years. What ties these phenomena together is their role as cosmic engines. Nebulae recycle matter, star clusters organize it, and both shape the architecture of galaxies. Without them, the universe would be a static sea of darkness. Instead, they weave a story of perpetual change, one where destruction fuels creation, and every ending plants the seeds for a new beginning. To understand how nebulae form, we need to step into the chaotic workshop of the cosmos, where nothing is ever truly at rest. Picture a massive star, many times larger than our Sun, burning through its nuclear fuel at a furious pace. When such a star nears the end of its life, it doesn't just flicker out, it erupts in a cataclysmic supernova, hurling its outer layers into space at unimaginable speeds. These expanding shockwaves, laden with heavy elements, collide with surrounding gas, compressing and heating it until it begins to glow. This is how supernova remnants like the Veil Nebula come to life, an intricate lacework of gas illuminated by the dying breath of a star. But not all nebulae are born from destruction. Some, like the iconic Orion Nebula, emerge from vast molecular clouds, cold, dense regions where gravity slowly pulls gas and dust together. Over thousands of years, pockets within these clouds collapse under their own weight, forming protostars. As these young stars ignite, their intense radiation strips electrons from nearby hydrogen atoms, causing the gas to fluoresce in brilliant reds and blues. These emission nebulae act as cosmic lighthouses, their colors revealing the elemental makeup of the gas: hydrogen glowing red, oxygen shining blue-green. Then there are the dark nebulae, the shadowy architects of the cosmos. These dense, dusty regions block the light from stars behind them, appearing as inky voids against the starry backdrop. Yet within their depths, new solar systems take shape. The Horsehead Nebula, for example, isn't just a striking silhouette. It's a stellar nursery where gravity quietly molds gas into future stars. The forces shaping these nebulae are as dynamic as the structures themselves. Stellar winds from newborn stars carve cavities in the gas, while magnetic fields twist and channel the chaos into delicate filaments. Shockwaves from nearby supernova can trigger new waves of star formation, turning destruction into creation. It's a cycle as old as the universe itself, one where the end of one star becomes the beginning of countless others. Gravity works like a cosmic choreographer, silently pulling the strings behind the dazzling spectacle of star clusters. Picture a vast, swirling cloud of gas and dust drifting lazily through space. Left alone, it might simply linger for eons, but gravity has other plans. Bit by bit, it tugs these scattered particles together, compressing them until the pressure becomes unbearable. Then, like a match struck in the darkness, nuclear fusion ignites and a star is born. But gravity doesn't stop there. It binds these newborn stars into families, creating the breathtaking clusters we see scattered across the night sky. Take open clusters, for example, like the famous Pleiades, a glittering group of young stars that seem to huddle together against the cosmic cold. These clusters are the universe's way of showing us stellar siblings, born from the same gas cloud and still loosely holding hands. But they won't stay this way forever. Over millions of years, the gentle gravitational pull of passing stars and galactic tides will gradually pull them apart, scattering them across the galaxy like seeds in the wind. Globular clusters, on the other hand, are the elders of the cosmos, ancient, tightly packed spheres of stars that have survived for billions of years. These clusters are so dense that in their cores, stars are crammed shoulder to shoulder, separated by mere light weeks instead of light years. Their gravity is so strong that even the relentless pull of the galaxy itself can't tear them apart. This makes them cosmic time capsules, preserving the chemical makeup of the early universe. By studying the light from these stars, astronomers can read their elemental fingerprints, revealing secrets about how galaxies formed and merged in the distant past. But gravity's role doesn't end with just holding stars together. It shapes their destinies in ways we're only beginning to understand. In the crowded cores of globular clusters, stars can collide or even merge, creating bizarre stellar hybrids. Some clusters harbor black holes lurking in their hearts, their immense gravity warping the orbits of nearby stars. Others, like Omega Centauri, might even be the stripped-down cores of small galaxies swallowed by our Milky Way long ago. And here's the most astonishing part. These clusters aren't just relics of the past, they're actively shaping the future. As they orbit galaxies, their gravity tugs on surrounding gas, triggering new waves of star formation. They act as cosmic lighthouses, their ancient stars illuminating the history of the universe, while their gravity continues to sculpt the galaxies around them. So the next time you gaze at a star cluster, remember, you're not just seeing a random scattering of lights, you're witnessing gravity's masterpiece, a living testament to the forces that built the cosmos itself. Deep within the glowing heart of a nebula, hidden behind veils of dust and gas, lies one of the universe's most breathtaking processes, the birth of stars. These stellar nurseries are anything but peaceful. Imagine a maelstrom of gas, superheated to thousands of degrees, swirling in a violent ballet where gravity and radiation battle for dominance. Every second, pockets of hydrogen collapse under their own weight, growing denser and hotter until, like a light flickering on in the darkness, nuclear fusion ignites and a star is born. The Orion Nebula offers us a front-row seat to this cosmic spectacle. Here, newborn stars blaze to life, their fierce ultraviolet radiation sculpting the surrounding gas into ethereal pillars and cavernous voids. But look closer, and you'll see something even more astonishing: protostars, still wrapped in their dusty cocoons, voraciously devouring material from the disk of gas swirling around them. Sometimes, this feeding frenzy becomes so intense that twin jets of superheated plasma burst from the star's poles, shooting light years into space like cosmic blowtorches. These jets are nature's way of balancing the books. Without them, a young star's spin would tear it apart before it could even properly form. Not all stars emerge from this chaos equally. Some, like red dwarfs, are frugal with their fuel, burning so slowly they could outlast the universe itself. Others, like blue giants, live fast and die young, blazing with a brilliance millions of times stronger than our sun. What determines their fate? A delicate tug of war between gravity pulling inward and radiation pressure pushing outward. If gravity wins, the star grows. If radiation prevails, the surrounding gas disperses, cutting off the star's supply. It's a cosmic lottery where the stakes are nothing less than the future of solar systems. And that's the real magic of these nurseries. They don't just make stars. They forge the very ingredients of planets and, ultimately, life. The same swirling disks of gas feeding newborn stars also clump together into planets, asteroids, and comets. Heavy elements like carbon, oxygen, and iron, cooked in the hearts of long-dead stars and scattered by supernova, find their way into these disks, becoming the raw materials for rocky worlds like Earth. Every atom in your body, every mountain on our planet, even the air we breathe, all of it was once part of this star-forming chaos. Yet for all their violence, these nurseries are fleeting. Within a few million years, a blink in cosmic time, the brightest stars will blow away their birth clouds with their stellar winds, ending the era of creation and scattering the remaining gas across space. But even then, the cycle continues. That dispersed material will eventually drift into another nebula, another nursery, where gravity will once again work its magic, weaving new stars from the ashes of the old. It's a story without end, a reminder that in the grand tapestry of the cosmos, death is just another word for rebirth. There's a moment in every massive star's life when the cosmic scales tip, when the outward push of nuclear fusion can no longer withstand the crushing weight of gravity. And in that instant, the star doesn't just die, it becomes something far more spectacular. A supernova isn't merely an explosion, it's the universe's most extreme alchemy lab, where ordinary elements are forged into gold, uranium, and other heavy metals in the span of seconds. The energy released is almost beyond comprehension. A single supernova can outshine an entire galaxy for weeks, blasting particles at nearly the speed of light. Take the Crab Nebula, that twisted web of glowing filaments we see today. What we're witnessing is the aftermath of a star whose death was recorded by Chinese astronomers in the year 1054. Nearly 1,000 years later, its remnant still crackles with energy, powered by a rapidly spinning neutron star at its core, a cosmic dynamo so dense that a single teaspoon of its material would weigh billions of tons on Earth. This pulsar's fierce magnetic fields whip surrounding electrons into frenzied spirals, making the entire nebula glow like a celestial ghost. But here's the paradox: these cataclysms don't just destroy, they create. When a supernova's shockwave slams into nearby molecular clouds, it squeezes them like an accordion, triggering avalanches of star formation. The heavy elements forged in the explosion, oxygen, silicon, iron, are hurled into space, becoming the building blocks for rocky planets. That gold in your jewelry, it was likely born in the heart of a dying star, then scattered across the galaxy by a supernova's fury. These remnants also serve as cosmic crash test sites, revealing physics we could never replicate on Earth. Some collapse into neutron stars, where matter is compressed so tightly that protons and electrons merge into neutrons. Others might form black holes, warping space-time so severely that not even light escapes. By studying how these objects interact with their surroundings, like the way the Cassiopeia, a remnant, accelerates particles to near light speed, we're decoding the universe's most extreme conditions. Yet for all their violence, supernovae are astonishingly precise. The very elements they scatter are what allow new stars and life to emerge. It's a cycle of destruction and rebirth written into the fabric of the cosmos, where every ending plants the seeds for countless beginnings. So when you look at a supernova remnant, you're not just seeing a stellar graveyard. You're witnessing the universe's way of turning death into the raw materials for life itself. While gravity may be the most obvious sculptor of nebulae, it's far from the only force at work. Hidden beneath their swirling colors lies an invisible web of magnetic fields, threading through the gas like cosmic puppet strings. These fields aren't just passive observers, they actively shape how material moves, channeling ionized particles into intricate filaments and preventing gas clouds from collapsing too quickly. In the famous Eagle Nebula, where towering pillars stretch light years into space, magnetic fields act like cosmic scaffolding, helping these fragile structures withstand the relentless radiation from nearby stars. Without this invisible framework, these celestial spires would have dissipated eons ago. Then there's the transformative power of starlight itself. Massive young stars don't just illuminate nebulae, they blast them with ultraviolet radiation so intense it strips electrons from atoms, creating vast bubbles of ionized gas. This process, called photoevaporation, slowly erodes nebulae from the inside out, carving out cavernous voids and leaving behind those iconic pillars we see in Hubble images. The Horsehead Nebula's distinctive shape, That's starlight at work, a cosmic shadow cast where dense dust resists the radiation's relentless push. But perhaps the most mesmerizing force is turbulence, the same chaotic energy that creates whirlpools in rivers, just scaled up to interstellar proportions. Within nebular clouds, supersonic gas currents collide, creating fractal patterns that repeat from the largest scales down to the smallest. This isn't random chaos, it's a signature of how energy cascades through the cosmos, with eddies within eddies shaping the birthplaces of stars. The Tarantula Nebula's intricate web-like structure showcases this perfectly, where turbulent flows have created a labyrinth of star-forming regions. Deciphering these forces requires more than just powerful telescopes. Supercomputers now run sophisticated simulations that recreate nebula physics down to the movement of individual particles. These virtual laboratories reveal surprises, like how magnetic fields can launch jets from newborn stars, or why some nebulae develop bizarre, twisted shapes. Each discovery peels back another layer of the universe's hidden blueprints, showing us that behind every celestial masterpiece lies an intricate dance of forces we're only beginning to understand. What makes this truly remarkable is how these processes aren't isolated. They interact in ways that constantly reshape the cosmic landscape. A magnetic field redirects a stellar wind, which triggers turbulence, which concentrates gas into new stars. It's this feedback loop that turns simple clouds into the complex, evolving tapestries we admire. So when you next gaze at a nebula's photograph, remember, you're not just seeing a pretty cloud. You're witnessing the universe's most sophisticated physics laboratory, where invisible forces collaborate to create the building blocks of worlds. Globular clusters are the universe's time capsules, dense, shimmering spheres of stars that have witnessed nearly the entire history of existence. Imagine a structure so ancient that when its light first began traveling toward us, the Milky Way itself was still taking shape. These clusters aren't just old, they're relics from an era when the cosmos was a vastly different place, a time before galaxies had fully formed, before most of the elements we know existed. Their stars burn with a purity rarely seen elsewhere, composed almost entirely of hydrogen and helium, the raw ingredients of the Big Bang. This lack of heavier elements tells us something extraordinary. These stars were born from nearly pristine gas, untouched by the chemical enrichment of later supernova. Take Omega Centauri, the largest globular cluster orbiting our galaxy. With over 10 million stars packed into a region just 150 light-years across, it's a stellar metropolis where night skies would blaze with countless suns. But what's truly remarkable is what we've learned from its chemistry. Unlike younger stars, which contain traces of iron, carbon, and oxygen forged in stellar furnaces, Omega Centauri stars are overwhelmingly simple cosmic fossils preserving the elemental makeup of the early universe. Some astronomers even suspect it might not be a cluster at all, but the remnant core of a dwarf galaxy torn apart by the Milky Way's gravity billions of years ago. Then there's the mystery of their survival. How have these clusters endured for 12 billion years in a universe where collisions and tidal forces routinely shred structures apart? The answer lies in their incredible density. Gravity binds their stars so tightly that even the gravitational pull of an entire galaxy can't easily disrupt them. But there's another invisible force at work, dark matter. While globular clusters themselves don't contain much of it, their orbits around galaxies trace the distribution of this elusive substance, helping astronomers map its presence. In this way, these ancient star clusters aren't just time machines, they're also cosmic detectives, revealing secrets about the unseen scaffolding of the universe. Their longevity also hints at a quieter, more stable past than we once imagined. Unlike the chaotic mergers and collisions that shaped galaxies, globular clusters seem to have avoided violent encounters, drifting in the halos of galaxies like distant sentinels. This stability makes them ideal laboratories for studying stellar evolution, because all their stars formed around the same time from the same material. Differences between them, like brightness or color, can only be due to their mass and age, eliminating variables that complicate studies of younger star groups. Perhaps most astonishing is what they tell us about the universe's infancy. The mere existence of such ancient, tightly bound clusters suggests that the early cosmos was far more structured than we thought. To form objects this dense so soon after the Big Bang, matter must have clumped together with incredible efficiency, challenging our models of how cosmic structures emerge. Some clusters even contain multiple generations of stars, hinting at prolonged periods of star formation in the universe's first chapters. And yet, for all their resilience, globular clusters aren't immortal. Over time, gravitational interactions slowly strip away their outer stars, leaving behind a denser core until, eventually, even that dissolves. But this process takes tens of billions of years, longer than the current age of the universe. So for now, these ancient marvels continue their silent orbits, their light carrying stories from a time when the cosmos was young and the first stars were just beginning to shine. Open clusters are the shooting stars of cosmic structures, brilliant, fleeting, and full of youthful energy, while globular clusters persist for billions of years like ancient monuments. Open clusters are more like sparks from a campfire, blazing brightly before scattering into the darkness. Take the Hyades, that familiar V-shaped group in Taurus. At just 625 million years old, it's already showing signs of drifting apart, its stars loosening their gravitational embrace as they respond to the Milky Way's tidal forces. Within another few hundred million years, these sibling stars will have gone their separate ways, their bond erased by the relentless pull of the galaxy. Yet in their short lives, open clusters hold invaluable clues about stellar evolution, because all their stars formed from the same cloud of gas and dust at roughly the same time. They're perfect laboratories for comparing how stars age differently based on mass. The Pleiades, for instance, showcase this beautifully hot blue giants burning ferociously alongside smaller, cooler stars that will outlive them by trillions of years. Their shared origin eliminates variables, letting astronomers isolate how mass alone dictates a star's fate. Some clusters, like the Beehive, carry chemical fingerprints of their birth. Nebula trace elements that reveal the composition of the cloud that birthed them. These cosmic breadcrumbs allow us to reconstruct stellar nurseries long since dispersed. Others, like the double cluster in Perseus, are so young they still glow with the residual light of their formation, their hottest stars ionizing what little gas remains around them. But perhaps their greatest gift is how they map the galaxy's spiral arms. As open clusters drift apart, their stars retain subtle similarities in motion, like siblings raised in the same home before setting off on different paths. By tracking these stellar trajectories, astronomers can trace where the clusters formed, revealing how our galaxy's spiral structure has shifted over time. The fact that we find so many open clusters along the Milky Way's arms isn't coincidence, it's proof that these regions are where star formation thrives, even today. Their transience is a reminder that the universe is never static. Every cluster's dissolution seeds the galaxy with new stars, each carrying elements forged in their shared birthplace. So while they may not last, their legacy endures in the planets that form around their scattered stars, and in the chemical enrichment they leave behind. Open clusters don't just show us how stars are born, they show us how the galaxy grows. The brilliant colors painting nebulae across the cosmos aren't just for show, they're the universe's way of revealing its deepest secrets. That deep crimson glow dominating so many nebula images, That's hydrogen gas, the universe's most abundant element, fluorescing under the intense ultraviolet radiation from nearby stars. When these high-energy photons strike hydrogen atoms, they excite the electrons, which then release that energy as distinctive red light, a process called hydrogen alpha emission. It's like nature's neon sign, advertising star-forming regions across thousands of light years. But shift your gaze to the sapphire hues swirling through nebulae like the Iris Nebula, and you're seeing something entirely different. These cooler blue tones come from starlight scattering off microscopic dust grains, cosmic mirrors reflecting the brilliance of young, hot stars. The smaller the dust particles, the more efficiently they scatter blue light, just like Earth's atmosphere makes our sky appear blue. This interplay of light and dust reveals the texture of these stellar nurseries, showing where material is dense enough to birth new planetary systems. Then there are the emerald whispers of oxygen glowing faintly in nebulae like the Ring Nebula. When doubly ionized oxygen atoms relax back to lower energy states, they emit that characteristic blue-green light, a spectral signature so precise it acts like a cosmic barcode. These oxygen-rich regions often trace the outer shells of dying stars, where ultraviolet radiation has stripped away electrons, leaving behind ionized gas that tells the story of a star's final act. But not all nebulae dazzle with color. Those inky black veins cutting through the glowing clouds, those are Bok globules, dense knots of gas and dust so thick they block all light behind them. These cosmic shadows aren't empty, they're stellar wombs where gravity works unseen, compressing material until new stars ignite. The Horsehead Nebula's famous silhouette demonstrates this perfectly, its dark molecular cloud backlit by the glowing hydrogen of IC434. Spectroscopy transforms these colors into scientific gold. By breaking nebular light into its component wavelengths, astronomers identify elements with forensic precision. An emission line at 656.3 nanometers, that's hydrogen, 495.9 and 500.7 nanometers. Oxygen's calling card. This technique even reveals motion redshifted or blue-shifted lines, show whether material is rushing toward us or fleeing away at thousands of miles per second. What's astonishing is how these colors chronicle galactic recycling. The red hydrogen signals new stars being born. The blue reflected light shows where their radiation pushes on surrounding dust, and the green oxygen marks the ashes of dead stars enriching the cosmos. Together, they weave a story of continuous transformation, where every hue represents a different chapter in the eternal cycle of stellar life and death. Far from mere decoration, these colors are the universe's way of keeping its own diary, written in light across the vastness of space. Imagine a star like our Sun, not with a violent explosion, but with a slow, luminous sigh, a final act of cosmic artistry before fading into darkness. This is the story of planetary nebulae, some of the most misunderstood yet breathtaking objects in our galaxy. Their name is a historical accident coined by 18th century astronomers who saw their round shapes through primitive telescopes and mistook them for distant planets. But we now know these glowing shells represent something far more profound, the last chapter in the life of an ordinary star. When a star like our Sun exhausts its nuclear fuel, it doesn't go quietly. In its death throes, it swells into a red giant, its outer layers puffing away like smoke from a candle. Radiation from the exposed core, now a searing white dwarf, illuminates this ejected gas, creating a radiant nebula that can stretch light years across space. The Ring Nebula, one of the most studied planetary nebulae, showcases this process with near-perfect symmetry, its glowing blue-green oxygen and red hydrogen forming a celestial bullseye. But not all planetary nebulae are so orderly. The Helix Nebula resembles a colossal eye staring across space, its intricate filaments and radial streaks revealing turbulent forces at work. What's truly remarkable is the diversity of shapes these nebulae take. Some, like the Butterfly Nebula, exhibit spectacular bipolar jets, twin lobes of gas hurled outward by the dying star's intense magnetic fields. Others, like the Cat's Eye Nebula, contain concentric shells, like tree rings recording successive waves of material ejected over thousands of years. These structures aren't just beautiful, they're cosmic fingerprints encoding details about the star's final convulsions. Astronomers now believe companion stars or even planets may sculpt these outflows, their gravitational tugs warping the stellar winds into intricate patterns. But planetary nebulae aren't just celestial gravestones, they're galactic recyclers. As they expand, they flood space with carbon, nitrogen, and other life-essential elements cooked in the star's core. A single planetary nebula can eject up to half the star's mass, dispersing it into the interstellar medium where it will eventually form new stars, planets, and perhaps even life. That carbon in your DNA, some of it likely passed through a nebula like this long before Earth existed. Yet for all their grandeur, planetary nebulae are fleeting. Their glowing gas dissipates into space within 50,000 years, a blink in cosmic time. The white dwarf at their heart cools over billions of years, fading into obscurity. This is the fate awaiting our Sun, a reminder that even the most familiar stars are part of an unending cycle of creation and renewal. By studying these nebulae, we're not just uncovering the death of stars, we're tracing the journey of the very atoms that make up our world. Dark matter doesn't just lurk in the shadows of the cosmos, it actively sculpts the destiny of star clusters in ways we're only beginning to unravel. Picture a globular cluster, its ancient stars bound together by gravity, drifting through the halo of a galaxy. What we can't see but know must be there is the invisible hand of dark matter, its gravitational pull shaping the cluster's orbit and even influencing how stars move within it. In dwarf galaxies like the Fornax system, where dark matter outweighs visible matter by a staggering ratio, this unseen force compresses gas clouds like an invisible vice, triggering bursts of star formation that wouldn't occur otherwise. These clusters become cosmic breadcrumbs, tracing the distribution of dark matter, much like iron filings reveal the shape of a magnetic field. Some of the most compelling evidence comes from the bizarre behavior of certain globular clusters. Take NGC 241, orbiting our neighboring Triangulum galaxy. Its stars move faster than gravity from visible matter alone can explain, as if something unseen were tugging at them. This anomaly suggests the cluster might be embedded in a subhalo of dark matter, a relic from when galaxies were first assembling. Yet other clusters, like those in the Andromeda Galaxy, show no such dark matter fingerprints, their stars moving precisely as Newton's laws predict. This contradiction has astronomers puzzled. Why do some clusters appear drenched in dark matter while others are completely devoid of it? One theory points to their violent origins. During the cosmic chaos of galaxy formation, clusters born in the turbulent cores of dwarf galaxies may have carried dark matter with them like celestial hitchhikers. Others, formed in colliding gas clouds within giant galaxies, might have been stripped of their dark matter by tidal forces. The Palomar 5 cluster tells this story vividly. Its stars are so loosely bound that they stream across space in a stellar river, likely the aftermath of repeated encounters with the Milky Way's dark matter halo. These interactions aren't just destructive, they're transformative, altering the cluster's structure over billions of years. The implications go far beyond star clusters. If dark matter truly influences their evolution, then studying these systems could reveal fundamental properties of the universe's most mysterious substance. For instance, the way dark matter particles theoretically interact with each other, whether they collide, scatter, or simply pass through one another, could explain why some clusters retain dark matter while others lose it. Some researchers even speculate that certain ultra-diffuse galaxies, which appear to lack dark matter entirely, might have had it stripped away by encounters with larger galaxies, leaving behind ghostly star clusters as evidence. What makes this mystery so thrilling is how it connects the very large to the very small. The motions of stars within a cluster could hint at dark matter's particle nature, whether it's cold and slow-moving or warm and more energetic. Discrepancies between predicted and observed star distributions in clusters have even led some scientists to reconsider gravity itself, proposing modifications to Einstein's theory of general relativity. Every globular cluster becomes a natural laboratory, testing our deepest theories about the fabric of reality. So the next time you gaze at a star cluster, remember, you're not just seeing a collection of ancient suns. You're witnessing the visible edge of an invisible cosmos, where dark matter's secrets are written in the paths of stars. Unlocking these mysteries won't just tell us about clusters, it might finally illuminate the dark heart of the universe itself. Deep within the swirling cores of the densest nebulae, nature orchestrates its most extreme stellar births where massive stars, those cosmic titans dozens of times heavier than our sun, come roaring into existence. These aren't gentle births. Imagine a storm where gravity and radiation wage war, where collapsing gas clouds must battle the very stars they're trying to create. The violence begins when a dense knot of gas, hundreds of times the mass of our sun, starts collapsing under its own weight. As it shrinks, temperatures skyrocket, and the protostar at its core begins to shine. But unlike smaller stars, its light doesn't nurture. It obliterates. The moment nuclear fusion ignites, the star's fierce ultraviolet radiation and supersonic stellar winds act like cosmic blowtorches, blasting away the surrounding gas that feeds it. This self-destructive paradox is why massive stars are so rare. They risk starving themselves before they fully form. The Orion Nebula offers a front-row seat to this chaos. Near its trapezium cluster, a handful of young behemoths, some 50 times the sun's mass, have carved vast cavities in the gas with their radiation. These bubbles, stretching light years across, aren't just empty space. Their shockwaves compress nearby gas into new generations of stars, even as they halt star formation elsewhere. It's a feedback loop of creation and destruction, where one massive star's birth can dictate the fate of an entire stellar nursery. Yet the real puzzle lies in how these giants defy their own self-sabotage. For gravity to win against such intense radiation pressure, theorists suggest two possibilities. Either the collapsing gas must be incredibly dense, piling on mass faster than the star can repel it, or multiple smaller stars merge in a violent cosmic collision. The Tarantula Nebula's R136 cluster supports the latter idea. Its brightest star, weighing over 250 solar masses, might be the product of such a stellar merger. Their lives burn bright and short. A star like our sun has 10 billion years to quietly fuse hydrogen. A massive star races through its fuel in just a few million. But in death, they become cosmic alchemists. Their supernova explosions forge elements like gold, platinum, and uranium, scattering them across galaxies. The Carina Nebula's Eta Carinae, a hypergiant on the brink of detonation, reminds us of this inevitable fate. When it goes supernova, its ejected material will someday seed new planets and perhaps life. What's most astonishing is how these rare stars dominate their environments. Their winds shape nebulae into intricate structures, their deaths trigger new star formation, and their heavy elements enrich entire galaxies. Without them, the universe would lack the ingredients for rocky planets, or life itself. Yet their formation remains one of astrophysics' greatest challenges, a reminder that even in the vastness of space, true giants walk a razor's edge between existence and self-destruction. Every atom in your body holds a story written in the fires of dying stars, a tale of cosmic resurrection that spans billions of years. Nebulae aren't just celestial scenery, they're the universe's recycling centers where stardust is endlessly forged, scattered, and reborn. Picture a supernova's final act, hurling iron, oxygen, and carbon into the void. These elements don't vanish, they drift through space until gravity gathers them into new molecular clouds, seeding the next generation of stars. The Orion Nebula, glowing vibrantly today, is built from remnants of stars that died before Earth even existed. Their ashes now fuel the birth of new solar systems, some of which may harbor planets and life just like ours. This recycling operates on scales that defy imagination. A single dying red giant can expel half its mass in slow, stellar winds, enriching surrounding gas with elements like silicon and sulfur. Planetary nebulae add to this celestial compost, their glowing shells dispersing nitrogen and carbon, essential ingredients for organic chemistry. Even the gentle outflows from stars like our Sun, though less dramatic, contribute over time. The Helix Nebula's intricate patterns, for instance, aren't just beautiful, they're a snapshot of our own star's future, a preview of how it will one day return its material to the galactic ecosystem. But the most violent contributors are undeniably supernova. When a massive star detonates, it floods space with heavy metals like gold and uranium, elements formed in the heart of the explosion itself. The Crab Nebula's swirling filaments, still expanding 1,000 years after the blast, carry these precious metals far and wide. Over eons, this enriched gas collapses anew, forming stars with higher concentrations of heavy elements, stars like our Sun, which formed from gas already peppered with the remnants of countless ancestors. Here's the marvel: this process is why Earth exists at all. The iron in our planet's core, the calcium in our bones, even the oxygen filling our lungs, all were forged in stellar furnaces and scattered by stellar deaths. The carbon in a diamond, the silicon in a computer chip, the gold in a wedding ring, each atom carries the legacy of stars that lived and died long before our solar system sparkled to life. This cycle isn't just poetic, it's measurable. Astronomers track elements like neon and argon in nebulae, finding ratios that match predictions of stellar nucleosynthesis. They observed newborn stars in regions like the Carina Nebula, their spectra revealing metals inherited from previous generations. Even the gas between stars, once thought pristine, is now known to be laced with these recycled materials. The implications stretch beyond astronomy. This continuous exchange of matter ties every living thing to the cosmos. Your body contains atoms that once circled distant suns, rode the shockwaves of supernova, and drifted for eons in dark nebulae. The universe doesn't waste, it transforms, and in that endless recycling we find our most profound connection to the stars, not just as observers, but as products of their fiery lives and deaths. Magnetic fields weave through the cosmos like invisible puppet strings, pulling the strings behind star formation in ways we're only beginning to understand. Picture a vast nebula, its gas clouds billowing like smoke, only instead of drifting randomly, every particle is subtly guided by these unseen forces. While gravity gets all the credit for pulling matter together, it's the magnetic fields that regulate the process, acting as cosmic traffic cops to prevent chaotic collapses. In the famous Taurus molecular cloud, Astronomers have mapped these fields using polarized starlight, revealing how they braid the gas into delicate filaments, like rivers of dust flowing along magnetic channels toward stellar nurseries. These fields don't just shape the birth of stars, they control the pace. Without their resistance, gas clouds would collapse into stars too quickly, burning through their fuel in a frenzied rush. Instead, magnetic tension slows the process, allowing matter to accumulate gradually. The result, more stable, long-lived stars like our Sun. In the Serpens Nebula, observations show how magnetic pressure creates dense pockets where star formation occurs in fits and starts, like bubbles forming in slowly simmering water. But their most spectacular influence appears in protostellar jets, those narrow beams of plasma shooting light years into space from newborn stars. These aren't random eruptions, they're precision guided by magnetic fields. As a young star spins, its magnetic field whips charged particles into twin jets aligned with its poles, funneling excess energy away so the star can keep growing. The Herbig-Haro objects in the Orion complex showcase this beautifully. Their glowing shock waves mark where these jets slam into surrounding gas, sculpting it like cosmic blowtorches. The field's reach extends even to planetary systems. A star's rotation, governed by magnetic braking during its formation, determines the architecture of its future planets. Too fast and protoplanetary disks shear apart. Too slow and material never clumps together. The surprising alignment of planetary orbits in systems like TRAPPIST-1 hints at how magnetic fields may have orchestrated their birth. Studying these invisible forces pushes technology to its limits. Telescopes like ALMA detect polarized millimeter waves to trace field lines, while supercomputer simulations recreate their interplay with gravity down to the quantum level. One breakthrough came when researchers noticed star-forming clouds align with the Milky Way's galactic magnetic field, proof that these forces operate across unimaginable scales. Yet mysteries remain. Why do some stars form in near-perfect isolation despite the field's filamentary guidance? How do turbulent gas motions sometimes overpower magnetic control? Each answer reveals how delicate the balance truly is, a reminder that star formation isn't just a battle between gravity and pressure, but a three-way dance where magnetic fields lead the steps. Among the tightly packed stars of a cluster where gravity rules supreme, a few rebels break free, launched into the void at speeds that defy cosmic convention. These runaway stars aren't just drifting, they're hurtling through space like bullets, their trajectories etched with tales of ancient violence. Take Zeta Ophiuchi, a blue giant racing through the galaxy at 54,000 miles per hour, its path marked by a glowing bow shocker, a cosmic wave rippling through interstellar gas. This star didn't choose solitude. It was catapulted from its birthplace by forces beyond imagination. The most dramatic ejections come from supernova explosions. Picture a binary star system where one star reaches the end of its life. When it detonates, the sudden loss of mass releases its companion like a slingshot, flinging it into the abyss at breathtaking speeds. The surviving star, now unshackled, carries the kinetic energy of that explosion forever. Mu Columbi, streaking across the constellation Columba, is one such fugitive, its motion tracing back to the Orion Nebula, where a cataclysmic supernova likely launched it 3 million years ago. But supernovae aren't the only culprits. Dense star clusters are gravitational minefields, where close encounters between stars can fling one into exile. Imagine two binary systems passing too close. The gravitational chaos that follows might eject a star at hypervelocity, while the others recoil in opposite directions. Astronomers have tracked stars like HD 49303, whose path suggests it was ejected from the Rosette Nebula's cluster after a violent gravitational tussle. These runaways aren't just celestial curiosities, they're forensic evidence. By tracing their paths backward, astronomers reconstruct the violent events that shaped them. Infrared observations of their bow shocks reveal how they interact with interstellar gas, heating it into glowing arcs that stretch light years ahead of them. The shockwaves they create can even trigger new star formation, turning their chaotic journeys into unintended acts of cosmic creation. What's most astonishing is their endurance. Some runaway stars, like the hypervelocity stars escaping the Milky Way's center, will never return, destined to drift between galaxies in eternal exile. Others, like A Aurigui, blaze through space, still glowing with the heat of their birth, their light a fleeting testament to the chaos that birthed them. These stellar outlaws challenge our assumptions about order in the cosmos, proving that even in the most tightly bound systems, chaos can rewrite destinies in an instant. Star clusters might look like uniform gatherings of ancient suns, but hidden within their light lies a chemical fingerprint as unique as a galactic DNA test. The idea that all stars in a cluster share identical origins has been shattered. Some globular clusters contain multiple generations of stars, each with distinct elemental signatures. Take Omega Centauri, where astronomers found stars with wildly varying levels of iron, oxygen, and even rare elements like europium. This isn't random variation, it's evidence of a dramatic past where the cluster's gas was enriched by supernova, then recycled into new stars before the raw material could fully mix. The universe, it seems, wasn't content with one stellar generation when it could have several. Open clusters tell a different but equally revealing story. While they are younger and less dense, their stars often carry subtle chemical differences, like siblings raised in the same home but with distinct tastes. The Hyades cluster, for instance, shows slight variations in elements like barium and strontium, suggesting its stars formed from pockets of gas that weren't perfectly uniform. Imagine a nebula not as a well-blended soup, but as a chunky stew where some regions were sprinkled with heavier elements from nearby supernova explosions. These chemical ingredients become cosmic breadcrumbs, leading us back to the conditions of their birth. What's truly groundbreaking is how these variations rewrite our understanding of cluster formation. The old textbook model, a single collapsing cloud birthing identical stars, can't explain clusters where some stars are rich in helium while others brim with nitrogen. Instead, we're seeing evidence of staggered star formation, where early generations of massive stars lived fast, died young, and polluted the cluster's remaining gas with their ashes. Gravity then compressed this enriched material into a second wave of stars, chemically distinct from their predecessors. The globular cluster NGC 2835 showcases this vividly. Its stars split into clear groups based on sodium and oxygen content, like layers in a cosmic cake. But the mystery deepens with clusters that defy expectations. Some, like M15, host stars with extreme variations in elements like magnesium and aluminum, yet show no correlation between these anomalies and the star's ages or positions. This suggests turbulent mixing processes we don't fully understand, perhaps collisions between gas clouds from different parts of the galaxy, or the influence of now vanished dark matter superhalos. Even more puzzling are iron complex clusters where stars differ not just in light elements but in heavy metals like iron, hinting at multiple episodes of supernova enrichment over tens of millions of years. The implications stretch far beyond star clusters. These chemical time capsules reveal how galaxies assembled their building blocks, When we find a cluster with stars that resemble the Milky Way's bulge more than its halo, it suggests that cluster might be a captured remnant of a devoured dwarf galaxy. Others, like Terzan 5, blur the line between globular clusters and galactic nuclei, their chemistry mirroring that of stars found near supermassive black holes. Every anomalous element ratio is a clue, a piece of evidence in astronomy's grand detective story about how structures emerged from the primordial cosmos. Modern telescopes have turned this field upside down. High-resolution spectrographs like those on the Very Large Telescope can detect element differences as subtle as a few % between stars. Combined with Gaia's precise stellar motions, we're now mapping not just what stars are made of, but where they acquired those materials, the result. A growing realization that star clusters aren't monolithic relics, they're dynamic archives, their chemical diversity recording everything from supernova shock fronts to collisions with gas clouds rich in intergalactic material. So the next time you gaze at a glittering star cluster, remember, those seemingly identical points of light are anything but. Each one carries elemental secrets about the cluster's violent youth, the turbulent medium it formed from, and perhaps even the cosmic accidents that shaped its destiny. In their atoms lies a story far richer than we ever imagined, one where chemistry becomes the key to unlocking the universe's deepest formation mysteries. Nebulae may paint the cosmos with their ephemeral beauty, but their existence is fleeting on the grand timeline of the universe. Consider the Orion Nebula. Its iconic glow, visible to the naked eye, masks a sobering truth. Within the next 100,000 years, the very stars it birthed will rip it apart. The trapezium cluster's blistering radiation is already evaporating its cradle, dispersing gas at speeds that could cross the continental United States in under 10 seconds. This isn't destruction so much as transformation, as the nebula's material spreads outward to fertilize distant regions of the galaxy. Supernova remnants face a different fate. The Crab Nebula's filaments, now racing outward at 9 million miles per hour, will gradually fade as their kinetic energy converts to heat, like embers cooling in a cosmic wind. Yet even as these structures vanish from view, their chemistry lingers. Every atom of oxygen in the Veil Nebula's delicate lacework was forged in the star's core, and when those filaments dissolve into the interstellar medium, they'll carry those elements to future stellar nurseries. Planetary nebulae, those glowing shells ejected by dying sun-like stars, have the briefest encore. The Helix Nebula's intricate patterns will dissipate within 50,000 years, a heartbeat compared to its 10 billion-year stellar life. But here's the marvel. Its expelled carbon and nitrogen are precisely what future organic molecules will require. The same forces erasing these nebulae are sowing the seeds for chemistry far more complex than their creators ever knew. What determines a nebula's lifespan? Density is key. The pillars of creation in the Eagle Nebula, though iconic, are ghosts of their former selves. Hubble's images captured light from a structure that likely disintegrated 6,000 years ago. Their tenuous gas couldn't withstand the stellar winds from nearby massive stars. Contrast this with the dark molecular clouds in Taurus, where cold, dense gas resists dispersion, preserving stellar nurseries for tens of millions of years. The universe recycles with ruthless efficiency. A single nebula's demise might fuel star birth in another galaxy quadrant, its atoms embarking on journeys spanning billions of years. Computer simulations tracking these flows reveal an astonishing pattern. Up to half the Milky Way's star-forming gas may have passed through previous generations of nebulae. When astronomers analyze the metal content in young stars like those in the Carina Nebula, they're effectively reading a cosmic genealogy written in spectral lines. This grand cycle holds clues to galaxies' futures. As the universe ages and nebulae exhaust their gas, star formation will gradually decline. The Large Magellanic Cloud offers a preview. Its irregular nebulae birthed stars chaotically in the past, but measurements show their current output slowing as available gas diminishes. Yet even in this twilight, new phenomena emerge. Ultrafaint dwarf galaxies like Leo T demonstrate how nebulae can persist in near stasis, their star formation flickering sporadically across cosmic epochs. The lesson written in nebulae's evanescence is profound. Transience fuels permanence. Their vanishing acts aren't endings, but intermissions in a show that's been running since the first stars ignited. The same forces scattering a nebula today will one day gather its atoms into something new, perhaps a star, a planet, or even the building blocks of life elsewhere in the cosmos. Their legacy isn't measured in millennia, but in the endless repurposing of their stardust across time and space. Deep in the heart of certain nebulae, where gas swirls in turbulent eddies, lurks one of the universe's most enigmatic architects, the black hole. Far from being mere voids, these gravitational monsters actively sculpt their surroundings, turning stellar graveyards into dynamic workshops of creation. Picture the Carina Nebula, its vibrant clouds glowing with young stars. Hidden within that chaos lies a silent giant, a black hole formed when a massive star collapsed without the fanfare of a supernova, its demise so complete it left no explosive remnant, just an invisible point of infinite density. What happens next defies intuition. As the black hole drifts through the nebula's gas, it doesn't just consume, it illuminates. Drawn by irresistible gravity, hydrogen and helium spiral toward the event horizon, compressing and heating to millions of degrees until they emit searing X-rays. These high-energy beams pierce the surrounding nebula like cosmic spotlights, ionizing gas clouds and painting intricate patterns of fluorescence. The microquasar SS-433, nestled in the galactic plane, demonstrates this vividly. Its jets, powered by a feeding black hole, stretch 40 times the solar system's width, energizing the nebula around it. But black holes don't stop at lighting up their neighborhoods. In dense star clusters like Messier 15, they play gravitational puppeteer. Over millennia, black holes sink to the cluster's core, their immense mass acting as an anchor that stabilizes the orbits of surrounding stars. This isn't just celestial housekeeping, it's a survival mechanism. Without a central black hole's influence, clusters could tear themselves apart through chaotic stellar interactions. The globular cluster NGC 3242 offers a stunning example. Its stars orbiting an invisible mass 10 times heavier than our Sun, a quiet guardian maintaining order amid stellar chaos. Yet their most surprising role lies in triggering new star birth. Counterintuitive as it seems, black holes can be midwives to solar systems. When a black hole's gravity compresses nearby gas clouds, it creates pockets of density ripe for star formation. The Tarantula Nebula's outskirts show evidence of this: filaments of gas stretched and squeezed by passing black holes, their distorted shapes giving rise to protostars where none should exist. Even more dramatic are the positive feedback scenarios seen in distant starburst galaxies, where black hole jets ram into molecular clouds, shocking them into collapsing into new stars. The interplay between destruction and creation reaches its peak in active galactic nuclei, where supermassive black holes drive colossal outflows. These winds, traveling at millions of miles per hour, sweep up nebula material like cosmic plows, piling it into dense shells that fragment into star clusters. The nearby Centaurus, a galaxy, reveals this process in action, its dust lanes peppered with young stars born from the turmoil of its central black hole's eruptions. Unraveling these connections requires cutting-edge tools. X-ray telescopes like Chandra catch the telltale signatures of accreting black holes hidden in nebulae, while radio interferometers trace their jets carving through star-forming regions. Simulations now show how intermediate mass black holes, long thought theoretical, might be the missing link between stellar remnants and their supermassive cousins. Each discovery peels back another layer of the paradox that the universe's most destructive forces are also, inexplicably, among its most creative. So the next time you admire a nebula's glow, consider what might lie unseen within it. Behind those veils of gas and light, black holes could be quietly orchestrating the birth of stars, the motion of clusters, and the chemical enrichment of galaxies. Their influence stretches far beyond their event horizons, weaving destruction and creation into a single, inseparable cosmic tapestry. Nebulae don't float through space untouched, they're cosmic chameleons, shaped by the galaxies they call home. Take a spiral galaxy like our Milky Way, its arms swirling with star-forming frenzy. Here, density waves like traffic jams in space compress gas as they move through the galactic disk, squeezing nebulae into existence like cosmic origami. The Eagle Nebula, with its iconic pillars of creation, owes its very structure to these rhythmic galactic pulses. Without the spiral arm's gravitational nudge, its gas might have drifted aimlessly, never reaching the critical density to birth stars. But venture into an elliptical galaxy and the story flips. These smooth, football-shaped giants lack the gas-rich arms of their spiral cousins. Their nebulae are few and far between, their stars aging quietly without the fireworks of new stellar nurseries. Why ellipticals are thought to be the products of galactic mergers, where violent collisions long ago heated and scattered their gas, leaving behind a graveyard of old stars with little material left to create new ones. The few planetary nebulae that do exist here, like those in Messier 87, glow like lonely embers in a fading fire. Then there are the galactic train wrecks collisions like the antennae galaxies, where two spirals smash together in a slow-motion ballet of destruction and rebirth. As their gas clouds collide, shockwaves rip through them, triggering frenzied bursts of star formation. Nebulae here don't just form, they explode into being, their birth rate skyrocketing as gravity turns chaos into creation. The tadpole galaxy's tail, stretched by a past encounter, is studded with such newborn clusters, each a testament to how violence can ignite life on cosmic scales. Even subtler forces leave their mark. The Milky Way's magnetic field, though invisible, threads through every nebula like a ghostly spiderweb, guiding the movement of charged particles and shaping how gas collapses. Cosmic rays high-energy particles racing through space alter nebula chemistry by breaking apart molecules and ionizing atoms, subtly shifting the balance of elements available for future stars. In the Rho Ophiuchi cloud, these processes are quietly at work, preparing the next generation of solar systems. What emerges is a revelation. Nebulae aren't just inhabitants of galaxies, they're products of them. A nebula in a quiet spiral arm evolves differently than one in a merging galaxy or a dormant elliptical. Their lifespans, shapes, even the types of stars they birth, are written in the gravitational tides, magnetic fields, and radiation baths of their galactic environments. This interplay is so profound that by studying a nebula's structure, astronomers can often reconstruct the history of the galaxy around it, like reading the life story of a forest in the rings of a single tree. The implications stretch across cosmic time. Early galaxies, smaller and more turbulent, would have hosted nebulae far more violent than those we see today. Their intense radiation and frequent collisions might have produced stars of unimaginable mass, whose brief lives seeded the universe with heavy elements faster than modern nebulae ever could. Meanwhile, in the distant future, as galaxies exhaust their gas and cease forming new stars, the era of brilliant emission nebulae will fade, leaving behind only the dim glow of planetary nebulae from dying suns. Yet even in this grand tapestry, surprises await. Ultra-diffuse galaxies like Dragonfly 44, almost invisible despite their size, challenge our assumptions. They contain nebulae far fewer than their mass suggests, hinting at galactic environments where gas behaves in ways we don't yet understand. Each of these cosmic outliers forces us to reconsider the delicate balance between a galaxy and the nebulae it hosts, proving that in the universe's workshop, context is everything. Globular clusters shouldn't care about galactic geometry. Their orbits ought to be as random as marbles spilled across a floor. Yet astronomers keep finding clusters moving in eerie synchrony, their paths aligned like dancers in a cosmic ballet. This isn't just odd, it's a violation of everything we thought we knew about how galaxies form. Take the Milky Way's outer halo, where a group of clusters orbits in a single, narrow plane, a pattern so precise it's as if some unseen hand arranged them deliberately. The odds of this happening by chance, less than 1 in 100. The leading theory points to galactic violence. When two galaxies collide, their globular clusters don't just scatter, they get dragged along in the wreckage, their orbits imprinted with the angle of impact. The Sagittarius dwarf galaxy, currently being torn apart by the Milky Way's gravity, offers a live demonstration. Its clusters are strewn along a curve tracing its death spiral, a celestial breadcrumb trail marking its final orbit. Over billions of years, these captured clusters may retain hints of their original alignment, like fossils preserving the geometry of an ancient collision. But dark matter complicates the story. Simulations suggest the Milky Way's halo isn't a smooth sphere. It's lumpy, with invisible tendrils stretching far beyond the visible disk. As clusters orbit, these dark matter filaments could nudge them into preferred planes, like marbles rolling along invisible grooves. The Large Magellanic Clouds clusters show tantalizing evidence of this, their motions hinting at an unseen structure warping their path. The real shock came when astronomers looked beyond our galaxy. In Andromeda, researchers discovered not 1 but 3 distinct planes of clustered orbits, layered like sheets of glass in a window. This can't be explained by a single collision. Instead, it suggests Andromeda devoured multiple smaller galaxies, each depositing clusters in different orientations. The most striking example is the giant elliptical galaxy Centaurus A, where clusters orbit in a vast, thin disk perpendicular to the galaxy itself, a configuration so unnatural it defies traditional formation models. These aligned clusters are more than orbital oddities, they're time machines. By reverse engineering their paths, astronomers can reconstruct galactic mergers that happened 10 billion years ago. The metal-poor clusters in the Milky Way's inner halo, for instance, move in ways that match simulations of our galaxy's first major collision, a cataclysm that may have defined its entire structure. Other clusters, like those in the bizarre polar ring galaxy NGC 4650, orbit at right angles to their host's disk, preserving the trajectory of some long-vanished interloper. Yet mysteries remain. Why do some clusters align while others, born from the same collisions, scatter randomly? How do dark matter subhalos sculpt these patterns without ripping clusters apart? Even more puzzling are isolated alignments, clusters moving together despite being separated by thousands of light years. The answer may lie in their birth conditions. Recent studies suggest aligned clusters might have formed in the stretched-out tidal tails of merging galaxies, where gas clouds collapse into stars under the same directional forces, imprinting their orbits with shared motion from birth. Every new discovery twists the plot further. The Gaia spacecraft's precise measurements recently revealed that some Milky Way clusters aren't just aligned, they're counter-rotating, moving opposite to the galaxy's spin. This could be the smoking gun of a head-on collision, where a smaller galaxy plunged through the Milky Way like a bullet, leaving its clusters spinning backward. Each of these cosmic clues forces us to rewrite galactic history, proving that the universe's past was far more violent and far more orchestrated than we ever imagined. So the next time you see a globular cluster gleaming in a telescope, remember, you're not just looking at a ball of stars, you're seeing a celestial compass, its motion encoding directions to events older than Earth itself. Their alignments are cosmic hieroglyphs waiting for us to crack their code. And when we do, they'll reveal not just how galaxies grew, but how the universe itself assembles its grandest structures, one careful, mysterious alignment at a time. Hidden within the delicate tendrils of every nebula, an invisible storm rages cosmic rays, the universe's silent sculptors. These aren't just random particles, they're atomic bullets fired from the aftermath of supernova, traveling near light speed with enough energy to punch through entire galaxies. When they slam into a nebula's gas, the impact is anything but gentle. Each collision strips electrons from atoms, ionizing the gas and kickstarting chains of chemical reactions that wouldn't occur otherwise. The Orion Nebula's outer edges reveal this process in action, where cosmic rays have transformed simple hydrogen molecules into ionized plasma, glowing faintly in X-rays, a ghostly signature of their passage. But their influence runs deeper than illumination. In the frigid hearts of dark nebulae like Barnard 68, cosmic rays act as cosmic matchmakers, nudging atoms together to form complex organic molecules. Methanol, formaldehyde, even amino acid precursors, all have been detected in these icy vaults, their creation fueled by the relentless bombardment of high-energy particles. It's a paradox. The same radiation that can shred DNA also provides the energy needed to assemble life's building blocks. The Rosette Nebula's molecular clouds showcase this delicate balance, where cosmic rays simultaneously destroy simple compounds and forge more intricate ones, like a celestial alchemist balancing destruction and creation. Some nebulae wear the scars of these interactions like crowns. The Gamma Cygni Nebula, named for the faint gamma-ray halo surrounding it, betrays the presence of cosmic rays colliding with gas at energies millions of times stronger than any particle accelerator on Earth. These gamma rays aren't just radiation, they're messengers, carrying encoded details about the magnetic fields threading the nebula. By mapping their glow, astronomers have traced invisible magnetic highways that guide both cosmic rays and star-forming gas, revealing how deeply interconnected these forces truly are. Yet cosmic rays don't just build, they also delay. In the sprawling Eagle Nebula, their relentless heating of gas creates pockets of turbulence that counteract gravity's pull, putting the brakes on star formation in certain regions. This explains why some nebula sections remain eerily quiet while others burst with stellar births. It's a cosmic tug of war, where the energy from long-dead stars determines where and when new ones will ignite. The Lagoon Nebula's uneven star distribution hints at this struggle, its western flank bristling with young stars while the eastern clouds linger in suspended animation, held back by cosmic ray pressure. The most tantalizing clue lies in their partnership with magnetic fields. As cosmic rays spiral along these invisible lines, they generate currents that can twist field lines into braids, structures visible in the Veil Nebula's filamentary wreckage. These braids, in turn, funnel more cosmic rays into specific zones, creating feedback loops that shape entire nebula ecosystems. Supercomputer simulations of the Carina Nebula show this dance in stunning detail, with cosmic ray streams carving cavities that channel stellar winds, effectively directing where new stars can and can't form. What makes this frontier so thrilling is its sheer unpredictability. The same cosmic rays that suppress star formation in one nebula might trigger it in another, depending on the gas density and magnetic environment. In the Tarantula Nebula's outskirts, they've been caught in the act of compressing gas just enough to tip the scales toward collapse, proving there's no universal rule, only an intricate web of contingencies. Even more astonishing are recent radio telescope observations suggesting cosmic rays might seed nebula gas with rare isotopes like aluminum-26, whose decay heats surrounding dust and alters the chemistry of emerging planetary systems. So the next time you gaze at a nebula's ethereal glow, remember, what you're seeing is only half the story. Behind every swirl of gas, beneath every radiant star, an unseen torrent of atomic particles is at work rewriting chemical recipes, tweaking stellar birth rates, and perhaps even setting the stage for life itself. These rays are the universe's hidden architects, proving that sometimes the most powerful forces are the ones we can't see at all. Reflection nebulae are the universe's most delicate illusionists, clouds of dust so fine they don't glow but instead borrow light, transforming the harsh glare of stars into something hauntingly beautiful. The Pleiades cluster, often called the Seven Sisters, wears its signature blue veil like a celestial shawl, not because its dust is blue, but because the tiny particles scatter starlight much like Earth's atmosphere scatters sunlight. Shorter blue wavelengths bounce off these interstellar grains more efficiently than red, painting the nebula in cool, ghostly hues. But what's truly fascinating isn't just the color, it's what these wisps reveal about the hidden architecture of space. Every reflected photon carries clues about the dust's composition, from the size of individual grains, often smaller than a wavelength of light, to their crystalline structure, some laced with carbon or silicates. Unlike their fiery emission nebula cousins, reflection nebulae are cosmic archivists. Their dust acts like a frozen snapshot of the raw materials left over from stellar births. The Iris Nebula, nestled in Cepheus, showcases this perfectly, its dust lanes backlit by a single star, revealing intricate tendrils that would otherwise vanish into the blackness of space. By analyzing how light polarizes as it scatters off these grains, astronomers can map magnetic fields threading through the nebula, tracing invisible forces that guide star formation. It's a subtle alchemy. The same dust that dims starlight also sculpts it into ethereal shapes, like sunlight filtering through a stained glass window. But these nebulae aren't just passive reflectors, they're active participants in cosmic recycling. The dust grains within them are far from uniform. Some are fluffy aggregates, while others are jagged fragments of shattered asteroids or the sooty remnants of long-dead stars. When starlight strikes them, it doesn't just bounce, it heats them slightly, causing them to emit faint infrared radiation. NASA's James Webb Space Telescope has caught this process in action within the Witch Head Nebula, where dust warmed by the brilliant star Rigel glows in thermal hues invisible to human eyes. This thermal whisper reveals something profound. These seemingly cold clouds are anything but inert. What makes reflection nebulae indispensable to astronomers is their role as cosmic sieves. The way they filter starlight exposes the presence of complex molecules clinging to dust grains, ices like water, methane, and ammonia that will one day become part of comets or planetary atmospheres. The Merope Nebula, part of the Pleiades, even shows signs of dust coagulation, where microscopic particles begin clumping together, taking the first tentative steps toward building planets. It's a process we'd never witness directly without the nebula's reflective curtain to illuminate it. Yet for all their quiet beauty, these nebulae are fleeting. The same starlight that graces them with color also spells their doom. radiation pressure gradually blows the dust away, dispersing it into interstellar space where it may eventually seed new nebulae. The Horsehead Nebula's reflection counterpart, IC 435, is already fraying at the edges, its dust evaporating under the relentless glare of nearby stars. This impermanence makes them celestial ghosts here just long enough to reveal the unseen, then vanishing without a trace, leaving behind only the echoes of reflected light and the promise of future worlds. Hidden within the glittering crowds of star clusters, binary systems play out their secret dances, gravitational waltzes that rewrite the rules of stellar life. These aren't just two stars orbiting each other, they're cosmic power couples whose interactions can reshape entire clusters. Picture a tight binary in the heart of a globular cluster, where an aging red giant transfers its outer layers to a voracious white dwarf companion. This stolen gas piles up until it triggers a thermonuclear explosion, a nova that outshines a million suns for weeks. The Kepler cluster's recorded nova of 1670 wasn't just a spectacle. It was a stellar theft in progress, a celestial heist captured by astronomers centuries before they understood what they were seeing. But binaries don't just steal, they transform. In the dense core of clusters like 47 Tucanae, stars are packed so tightly that gravitational encounters between binaries act like cosmic slingshots. A close pass can hurl one star away at breakneck speeds while its partner recoils deeper into the cluster's heart. These exchange interactions explain the hypervelocity stars streaking through our galaxy, lonely fugitives ejected from their birth clusters by the gravitational machinations of binary systems. The blue straggler stars found in ancient clusters tell an even wilder tale. These unusually young-looking stars, burning hot and blue amidst their elderly neighbors, are likely the products of binary mergers, two stars spiraling together until they become one, rejuvenated by the collision. The real magic lies in how these pairs regulate their communities. Binaries act as gravitational batteries, absorbing energy during close encounters and releasing it through their intricate orbits. Over eons, this process redistributes kinetic energy throughout the cluster, preventing core collapse and maintaining a delicate balance. The Messier 5 cluster demonstrates this beautifully. Its central binaries have effectively heated the surrounding stars, keeping the cluster fluffy instead of densely packed. Without these dynamic duos, globular clusters would age far differently, their stars collapsing into a chaotic central mass. Yet binaries also birth the universe's most exotic objects. Millisecond pulsars, neutron stars spinning hundreds of times per second, owe their ridiculous speeds to binary companions dumping mass onto them like cosmic spin instructors. The black hole binaries detected by gravitational wave observatories likely formed in clusters where frequent encounters paired these dark remnants. Even the mysterious X-ray sources peppering clusters like Omega Centauri trace back to binaries, where a compact object siphons gas from its neighbor, heating it to millions of degrees. What makes these systems indispensable is their role as natural laboratories. When astronomers watch a binary eclipse itself, the precise timing of dims and brightens reveals stellar masses, sizes, and temperatures with unmatched accuracy. The famous Algol system, known as the Demon Star for its eerie variability, taught us that stars can dramatically change size over their lifetimes, a revelation that came from tracking its eclipses over centuries. Modern telescopes have taken this further, catching binaries in the act of transferring mass, allowing us to test theories of stellar evolution in real time. The most astonishing binaries defy expectations altogether. In the Terzan 5 cluster, a pulsar orbits a sun-like star in a configuration so improbable it challenges our understanding of how such pairs form. Others, like the blue stragglers in NGC 1886, rotate so fast they're nearly tearing themselves apart, living proof of the violent mergers that created them. Each discovery peels back another layer of complexity, showing that in the crowded dance halls of star clusters, binaries aren't just participants, they're the choreographers, the troublemakers, and the keepers of cosmic order. Their gravitational tangos don't just shape their own fates, they orchestrate the evolution of the clusters that raised them, proving that in the cosmos, no star truly goes it alone. The next revolution in cosmic discovery is already unfolding, with telescopes like the James Webb Space Telescope peeling back the veil on nebula nurseries that were once invisible to us. Its infrared eyes pierce through the thickest dust clouds, revealing protostars so young they're still swaddled in their gaseous blankets. In the Orion Nebula, JWST has spotted water vapor and organic molecules swirling around infant stars, ingredients for future planetary systems that earlier telescopes couldn't detect. But this is just the beginning. The European Extremely Large Telescope, with its 39-meter mirror, will soon dissect starlight with such precision that we'll read the chemical composition of individual stars in distant clusters, tracing their origins back to specific nebula regions like cosmic genealogists. Simulations are leaping forward too, powered by supercomputers that can now model every gravitational nudge and gas collision in a forming star cluster. Where older simulations treated nebulae as smooth clouds, new algorithms capture the fractal chaos of real star birth turbulent eddies within eddies, where magnetic fields twist gas into braids thinner than our solar system. Researchers at the Harvard-Smithsonian Center for Astrophysics recently recreated the pillars of creation down to scales of a light year, revealing how ultraviolet light and stellar winds sculpt them in ways Hubble's snapshots never hinted at. These virtual laboratories are proving that what we see as serene cosmic landscapes are actually battlegrounds where forces vie for dominance at every scale. Citizen scientists are becoming indispensable partners in this golden age of discovery. Projects like Zooniverse's Milky Way project have volunteers combing through JWST overwhelming datasets, flagging oddities algorithms might miss, like the faint green glow of a previously unnoticed planetary nebula hidden behind the dust of Sagittarius. In 2022, a retired teacher in Norway spotted unusual dimming patterns around a star in the Butterfly Cluster, leading astronomers to confirm the first known exoplanet in a globular cluster. These crowdsourced breakthroughs hint at how much still lies beyond the reach of automated surveys, waiting for human curiosity to connect the dots. Yet the biggest revelations may come from mysteries we can't yet name. As instruments like the Square Kilometre Array radio telescope come online, they'll map the magnetic skeletons of nebulae in 3D, potentially uncovering why some gas clouds birth stars while others linger dormant. The Nancy Grace Roman Space Telescope's wide-field surveys could reveal failed nebulae vast gas reservoirs that never ignited into stars, challenging our theories of what triggers stellar birth. And lurking in all this data might be the answer to cosmology's greatest puzzle: how the first star clusters formed after the Big Bang before galaxies even existed. The coming decade won't just fill textbooks, it'll rip out chapters and rewrite them. From robotic telescopes scanning the skies nightly to AI that predicts supernova before they happen, we're on the verge of watching the cosmos evolve in real time. Every new instrument, every fresh perspective, brings us closer to understanding how nebulae and star clusters choreograph the grand ballet of galactic evolution, and where we, made from their stardust, fit into that eternal dance. Long before telescopes revealed their true nature, nebulae and star clusters were already etched into human consciousness, not as cosmic objects but as celestial stories. The Pleiades, that glittering knot of stars, wore different names in different skies. The Maori called them Matariki, marking the New Year's arrival. The Cherokee knew them as Anatsatsa, the dancing children. To the ancient Greeks, they were the 7 daughters of Atlas, forever fleeing Orion across the heavens. This cluster's universal presence in mythology isn't coincidence. Its tight grouping, visible even through light pollution, made it a cosmic landmark for agricultural calendars, navigation, and spiritual rites. The Maori planted crops when Matariki reappeared in dawn's glow, while Polynesian voyagers used its position to guide canoes across the Pacific's vast emptiness. Orion's nebula, that glowing sword hanging from the hunter's belt, carried equal weight. The Maya saw its haze as the embers of creation, a cosmic hearth where gods forged new stars. Norse legends interpreted its glow as the shimmering bridge to Valhalla. Even the 3 stars of Orion's belt served as celestial signposts. In ancient Egypt, their alignment with the pyramids of Giza mirrored the pharaoh's path to the afterlife, while Aboriginal Australians wove them into the tale of the 3 brothers who chased the emu across the sky. These weren't just imaginative tales, they were humanity's first astrophysics, attempts to explain the unexplainable using the language of the familiar. The cultural imprint runs deeper than myths. Nebulae's ethereal shapes have inspired artists for centuries, their forms echoing in the brushstrokes of Van Gogh's Starry Night and the swirling pigments of indigenous Australian dart paintings. The Lagoon Nebula's crimson glow found its way onto 17th century celestial maps as the Red Spider, while William Herschel's sketches of the Cat's Eye Nebula in 1787 blurred the line between scientific documentation and sublime art. This interplay birthed an unexpected legacy. The Hubble Space Telescope's images, though captured for research, have become cultural icons, their vibrant hues adorning album covers, fashion runways, and protest banners as symbols of unity and wonder. Today, these objects serve as bridges between eras and disciplines. The same Orion Nebula that guided Bronze Age sailors now helps astronomers study stellar birth, its light analyzed by spectrometers instead of storytellers. The Andromeda Galaxy, once called the Little Cloud by Persian astronomer Al-Sufi in 964, is now the yardstick for measuring cosmic expansion. Even the terminology we use, nebula, from the Latin for mist, carries echoes of pre-telescope observers straining to describe what their eyes couldn't resolve. Perhaps their greatest cultural power lies in what they represent, a shared inheritance. Whether you're a Navajo elder pointing out the Pleiades as Diliae, Hey, the seed stars, or a Japanese student spotting Subaru in a car logo, these patterns transcend borders. Modern light pollution may have dimmed their visibility, but their legacy persists in the names of spacecraft like the Orion capsule, in the timekeeping of festivals like Thailand's Loy Krathong, timed to a Pleiades alignment, and in the universal gasp when someone first sees the Orion Nebula through a telescope, realizing those ancient clouds are stellar nurseries. This continuity is no accident. Nebulae and clusters speak to something primal in us, their constancy against our fleeting lives, their light older than civilizations. They remind us that curiosity and awe are humanity's oldest companions, and that the urge to find meaning in the stars is perhaps our most enduring tradition. From the first storyteller who saw a hunter in Orion's stars to the astrophysicist mapping its nebula's magnetic fields, we're all part of the same unbroken conversation with the cosmos. At the violent hearts of galaxies, supermassive black holes don't just lurk, they orchestrate. These cosmic titans, weighing millions to billions of times our sun's mass, wield gravity like a sculptor's chisel, carving star clusters from the chaos around them. Picture the Milky Way's core, where the black hole Sagittarius, a star, reigns. Its occasional outbursts of energy don't just ripple through space. They slam into nearby gas clouds with enough force to squeeze them into stellar nurseries. The quintuplet cluster, a glittering family of young stars just 100 light-years from this gravitational monster, shouldn't exist by traditional logic. Yet there it glows, its massive stars defying the tidal forces that ought to tear them apart. The secret lies in the black hole's paradoxical nature. While its gravity can shred stars, its energy output creates shockwaves that trigger star birth. When jets of plasma erupt from the black hole's poles at near light speed, they plow through surrounding gas like cosmic bulldozers, piling it into dense shells. These compressed regions then collapse under their own weight, igniting clusters in the black hole's shadow. The starburst galaxy Messier 87 showcases this dramatically. Its central black hole's jet stretches thousands of light-years, yet along its edges, astronomers have spotted strings of newborn clusters like pearls on a cosmic necklace. Even more baffling are the clusters that orbit perilously close to these gravitational abysses. In the Andromeda galaxy's core, the cluster Mayol 2 orbits just a few light-years from its supermassive black holes, so near that tidal forces should have ripped it apart ages ago. The fact it persists suggests an incredible resilience, perhaps bound by its own dense gravity or shielded by dark matter. Other clusters, like those near the Milky Way's center, show bizarrely elongated orbits stretched by the black hole's pull into cosmic taffy. Their survival hints at a delicate balance between destruction and creation, where the same forces that threaten clusters also provide the pressure needed to forge them. These interactions aren't just local phenomena, they're galactic-scale feedback loops. As black hole jets heat and distribute gas, they regulate how and where clusters form across entire galaxies. The Phoenix Cluster, a gathering of galaxies 9 billion light-years away, reveals this process in overdrive. Its central black hole's outbursts have created a vast reservoir of cool gas, sparking the birth of thousands of stars per year, a stellar baby boom fueled by destruction. Conversely, when black holes go quiet, as in red and dead elliptical galaxies, cluster formation grinds to a halt. This yin-yang relationship suggests black holes don't just inhabit galaxies. They cultivate them, their explosive outbursts and gravitational might shaping stellar populations across cosmic time. The implications stretch back to the universe's infancy. Some of the oldest globular clusters, like those orbiting the relic galaxy NGC 1279, may have formed during primordial black hole feeding frenzies. Their unusual chemical abundances match predictions of gas enriched by early black hole activity. Even more provocative are theories linking intermediate mass black holes, the missing link between stellar remnants and supermassive giants, to the formation of some globular clusters. The recent discovery of a black hole in the cluster Omega Centauri lends credence to this idea, suggesting certain clusters might be stripped galaxy cores, their original supermassive black holes downgraded but still shaping their evolution. Unraveling this cosmic symbiosis requires telescopes that can peer through galactic dust to witness cluster formation in action. The James Webb Space Telescope's infrared vision has already caught black hole winds triggering star birth in the Cartwheel Galaxy, while radio arrays like ALMA trace how jets interact with molecular clouds. Each observation reveals another layer of complexity, like how magnetic fields channel black hole outflows into precise pathways, or why some clusters survive near black holes while others dissolve into stellar streams. What emerges is a radical reimagining of black holes not as destroyers but as cosmic architects. Their violent energies carve niches where stars can gather, their gravitational tides sculpt clusters into unexpected shapes, and their outbursts seed galaxies with the materials for future generations of stars. Far from being endpoints of cosmic evolution, supermassive black holes are catalysts, their influence woven into the very fabric of stellar communities. To understand how galaxies grow, we must first decipher this intricate dance between the universe's darkest giants and the glittering clusters they both menace and nurture. Star clusters glitter like celestial jewelry boxes, but their true treasures often lurk unseen. For every brilliant giant lighting up the telescope's view, there may be a dozen faint remnant stellar ghosts silently shaping the community around them. White dwarfs, the smoldering embers of sun-like stars, fade into obscurity over billions of years, their faint glow drowned out by younger neighbors. Yet their quiet presence anchors clusters gravitationally, their collective mass bending the paths of visible stars like invisible hands guiding a cosmic dance. The globular cluster Messier 4 tells this tale vividly. Its central regions contain thousands of white dwarfs detected only through their subtle gravitational influence and faint ultraviolet glow, outnumbering the cluster's bright stars nearly 2 to 1. More extreme remnants hide even deeper in the shadows. Neutron stars, those city-sized cinders left after supernova explosions, occasionally betray their presence through rhythmic pulses of radiation. The globular cluster Terzan 5 hosts at least 37 of these cosmic lighthouses, their beams sweeping across space like precision metronomes. Some, like the Black Widow pulsar, orbit companion stars so closely they're slowly evaporating them, a gruesome stellar vampirism playing out in X-ray wavelengths. Then there are the black holes, the ultimate invisible residents. In clusters like NGC 3200, astronomers have spotted stars whipping around unseen companions weighing several solar masses, dark gravitational anchors that could only be stellar mass black holes. The methods for uncovering these phantoms read like a detective's playbook. When an invisible compact object passes between Earth and a background star, its gravity bends light like a lens, a phenomenon called microlensing that briefly brightens the distant star's glow. The Hubble Space Telescope caught such an event in the cluster M22, revealing a rogue planet-sized object drifting between the stars. Gravitational wave observatories add another tool, listening for the space-time ripples produced when black holes or neutron stars collide. The signal JW19014 likely originated from a neutron star merger in a dense cluster environment, its distinctive chirp revealing secrets about matter under extreme conditions. Even more mysterious are the stray planets torn from their parent stars during close encounters. Simulations suggest a typical globular cluster could harbor thousands of these nomadic worlds, wandering the darkness between stars. Some might even retain thick atmospheres kept warm by internal heat or radioactive decay. The microlensing survey of Omega Centauri hints at their presence, with unexplained brightness fluctuations suggesting free-floating objects too small to be stars yet too large to be asteroids. What makes these hidden populations invaluable is the history they encode. The ratio of neutron stars to white dwarfs in a cluster reveals how many massive stars it once hosted. The spatial distribution of black holes traces the cluster's dynamical past, whether it suffered core collapse or maintained equilibrium. Even rogue planets carry clues, their numbers reflecting how often stellar close encounters disrupted protoplanetary disks in the cluster's youth. Like forensic scientists poring over a crime scene, astronomers piece together these subtle traces to reconstruct events that unfolded billions of years before telescopes turned toward the sky. The search continues with ever more ingenious techniques. ESA's Gaia mission tracks minute stellar wobbles that might betray unseen companions, while X-ray telescopes like Chandra hunt for the telltale glow of matter spiraling into black holes. Upcoming gravitational wave detectors will listen for the mergers occurring in these crowded environments, each collision a snapshot of the cluster's hidden demographics. Every discovery peels back another layer, reminding us that the sparkle of visible stars is just the surface glitter of far richer and stranger stellar communities. Star clusters hold time in their light not with gears and springs, but with the slow, inevitable march of stellar evolution. Picture a globular cluster like 47 Tucanae, its stars plotted on a graph of brightness versus color. What emerges isn't chaos but a striking pattern, a graceful curve where most stars cluster, then an abrupt turn-off point where the line suddenly drops. This isn't a glitch, it's the cluster's birth certificate. The turn-off marks the moment its most massive stars exhausted their hydrogen fuel and left the main sequence cooling into red giants. Since bigger stars burn faster, the turn-off's position reveals the cluster's age with astonishing precision. For 47 Tucanae, that number is 12 billion years older than Earth, older than the Sun, a relic from when the Milky Way was just taking shape. But stellar clocks don't stop there. White dwarfs, the dense embers of dead stars, provide a second hourglass. As these Earth-sized cores cool over billions of years, their fading glow acts like a cosmic thermometer. By measuring their temperature and luminosity, astronomers can estimate how long they've been cooling, an independent check on the turn-off method. The white dwarfs in the Hyades cluster, for example, tell a story of 700 million years, matching its turn-off age almost perfectly. When these methods agree, they cross-validate our understanding of stellar physics. When they disagree, as with the ancient cluster NGC 6397, where white dwarfs suggest an age a billion years younger than the turn-off, it forces us to rethink everything from nuclear reaction rates to the composition of primordial gas. The real power of these celestial chronometers lies in their reach. Globular clusters orbiting the Milky Way's outskirts, like Messier 92, push our cosmic calendar to its limits. Their ages 13.8 billion years neatly align with the universe's estimated birth in the Big Bang, a convergence so precise it helped cement our modern cosmological model. Yet even here, puzzles linger. Some clusters, like Omega Centauri, contain stars with wildly varying ages, suggesting they weren't born in a single event but grew through mergers, accumulating stars like cosmic snowballs over eons. Others, like the unusually young globulars in the Large Magellanic Cloud, defy expectations entirely, proving that cluster formation didn't end in the universe's youth but continues sporadically even now. These discrepancies aren't failures, they're opportunities. Each outlier forces us to refine stellar models, accounting for factors like rotation, magnetic fields, or exotic mixtures of elements in early stars. The Gaia spacecraft's precise measurements have added yet another layer, revealing that some clusters thought to be coeval actually host stars born hundreds of millions of years apart. This complexity transforms star clusters from simple clocks into intricate time capsules, their hands pointing not just to when they formed, but how, through violent mergers, gas accretion, or even collisions with dark matter substructures. What makes these natural chronometers indispensable is their universality. While Earth-bound clocks rely on human-made constants, the vibration of cesium atoms, the orbit of electrons, star clusters measure time through fundamental physics. The nuclear fusion rates etched into quantum mechanics, the gravitational collapse dictated by Einstein's equations. They're clocks built by the universe itself, ticking to rhythms far older than life, far older than planets, written in the slow dance of light and gravity across the deep time of the cosmos. The same swirling clouds of gas and dust that birth stars also hold the blueprint for their planetary systems, a cosmic recipe where the ingredients in a nebula determine what kind of worlds emerge from the chaos. Take the TRAPPIST-1 system with its 7 Earth-sized planets huddled close to a dim red star. The composition of those worlds, their iron cores, silicate mantles, and potential water reserves, was set in motion billions of years ago by the chemical makeup of the nebula that birthed them. Heavier elements like carbon and oxygen, forged in the hearts of long-dead stars and scattered by supernova, became the building blocks for rocky planets. Lighter gases like hydrogen and helium, dominant in younger nebulae, sculpted gas giants. This isn't just astronomy, it's galactic gastronomy, where nebulae act as master chefs, their elemental mixtures cooking up everything from molten lava worlds to icy ocean planets. Radiation from nearby stars adds another layer to this cosmic kitchen. In the Orion Nebula, ultraviolet light from massive young stars bombards protoplanetary disks, stripping away fragile atmospheres before they can fully form. Astronomers have spotted evaporating planets in these hostile nurseries, worlds like O Microscopii b, a gas giant losing its atmosphere so rapidly it trails a comet-like tail of ionized gas. Yet this same harsh environment might also spark life's precursors. Laboratory experiments show that ultraviolet radiation hitting nebula ices can create complex organic molecules, including amino acids. The pillars of creation, those iconic towers in the Eagle Nebula, might be more than just stellar nurseries. They could be probiotic factories, their shadowed crevices shielding delicate chemistry while their surfaces endure the very radiation that powers it. The fingerprints of these natal nebulae linger long after planets form. Jupiter's atmosphere contains argon and krypton isotopes that match predictions for the solar nebula's composition, a 4.5 billion-year-old snapshot preserved in a gas giant's swirling bands. Some exoplanets orbiting metal-rich stars show similar atmospheric signatures, their spectra revealing elements that point directly to the chemical abundance of their birth clouds. The mini-Neptune GJ1207b, for instance, has an atmosphere so thick with hydrogen and helium it's practically a piece of its primordial nebula frozen in time. But the interplay goes both ways. Planets themselves can reshape their nebulae during formation. As young worlds plow through their protoplanetary disks, their gravity carves gaps and rings patterns now visible in ALMA telescope images of systems like HL Tauri. These disturbances redirect gas flows, altering where future planets might form. In extreme cases, a massive planet's migration can scatter nearby material, truncating the disk and preventing sibling worlds from growing beyond a certain size. The absence of super-Earths in our solar system might trace back to Jupiter's early wanderings, its gravitational kicks clearing out the nebular real estate that could have housed larger rocky neighbors. What makes this cosmic dance so crucial is its role in planetary diversity. The Kepler telescope revealed a menagerie of exoplanets, hot Jupiters, water worlds, diamond planets, each a product of its nebula's unique conditions. A carbon-rich nebula might spawn worlds where silicon carbide replaces quartz in their crusts, while oxygen-dominated clouds could produce planets with deep global oceans. Even the nebula's lifespan plays a part. Those that dissipate quickly leave behind compact systems like ours, while longer-lived clouds allow gas giants to spiral inward, creating the tight orbital arrangements common around other stars. Nebulae don't just build planets, they set the stage for life's potential. The iron in Earth's core, the nitrogen in our air, even the phosphorus in our DNA, all were gifts from the solar nebula's carefully balanced chemistry. When we study distant star-forming regions like the Rho Ophiuchi complex, with its swirling organic molecules, we're glimpsing the same processes that made our existence possible. These glowing clouds are more than celestial art. They're the universe's workshop where physics, chemistry, and time conspire to turn stardust into worlds, and perhaps somewhere out there, into other beings gazing back at their own nebular origins with the same awe we hold for ours. Star clusters come in sizes as varied as the stars they contain, from sparse gatherings of a few dozen to dense metropolises hosting millions. The reason behind this staggering diversity isn't random chance. It's written in the birth conditions of their parent nebulae. Picture a vast molecular cloud, its gas so dense and turbulent that pockets collapse under their own weight like cosmic avalanches. In regions where gravity conquers all, outmuscling radiation pressure, magnetic fields, and even the heat of newborn stars, massive clusters take shape. The monstrous Omega Centauri, with its 10 million stars crammed into a sphere just 150 light-years across, likely began in one of these extreme environments, a gas reservoir so rich it could spawn stellar generations for eons. Yet not all clouds are created equal. Smaller clusters, like the Jewel Box in the Southern Cross, emerge from modest overdensities where gas trickles together rather than cascades. Without the violent turbulence needed to fragment a nebula into countless stars, these clusters grow slowly, their populations capped by the meager resources at hand. The Pleiades, with its glittering few thousand stars, is a perfect example, a stellar family born from a relatively quiet pocket of the Taurus molecular cloud, where gravity's grip was just strong enough to bind them but too weak to gather more. But birth conditions are only the opening act. Galactic forces take over as clusters age, sculpting their fates with relentless precision. In crowded regions like galactic centers, tidal forces, the gravitational tug of war between a cluster and its host galaxy, can strip away stars like leaves in a storm. Open clusters, fragile and loosely bound, often dissolve entirely within a few 100 million years, their stars scattering into the galactic disk. Globular clusters, though more resilient, aren't immune. The Milky Way's tides have stretched some into stellar streams like the Helmi Stream, a ghostly arc of stars that was once a cohesive cluster. Then there's the mystery of the outliers, clusters so massive they defy conventional origins. Omega Centauri's sheer size, its mixed stellar populations, and its unusual chemical fingerprints suggest it might not be a true globular cluster at all, but the surviving core of a dwarf galaxy devoured by the Milky Way long ago. Similarly, Mayol 2 in the Andromeda Galaxy, with its multiple generations of stars and complex dynamics, bears the hallmarks of a galaxy stripped down to its barest stellar bones. These cosmic imposters blur the line between clusters and galaxies, proving that the universe often resists our neat categories. The real revelation lies in what these size extremes teach us about star formation's limits. In the early universe, before galaxies took their modern shapes, clusters may have formed in even greater numbers and sizes, monstrous aggregations of stars since torn apart by cosmic time. Today's largest clusters are merely the survivors, the lucky few that avoided destruction. By studying them, we're glimpsing the upper boundaries of how stars can gather, the point where a cluster becomes something else entirely. And in that transition, we find clues to the grandest puzzle of all, how galaxies themselves assemble, one stellar family at a time. Some nebulae glow with more than just starlight. They burn with the echoes of cosmic violence from an era before our solar system flickered to life. Hidden in their spectral signatures are the forensic traces of ancient supernova, stellar explosions so powerful they forged elements not found in ordinary stars. The Crab Nebula, with its intricate lacework of filaments, isn't just a pretty remnant, it's a radioactive crime scene. It's gas laced with titanium, nickel, and cobalt isotopes that could only have been cooked in the heart of a dying star's catastrophic collapse. These elements don't just float idly, they serve as cosmic timestamps marking the moment over 1,000 years ago when a massive star's death scattered its guts across space. But some echoes are far older. In the vast Orion complex, astronomers have detected pockets of gas enriched with iron-60, a radioactive isotope with a half-life of 2.5 million years. Its presence is a smoking gun proof that a supernova detonated nearby within the last few million years, seeding the nebula with heavy elements just as new stars were beginning to form. Even more astonishing are the runaway stars like AE Aurigae, blazing through space with trajectories that trace back to Orion. These stellar fugitives were likely hurled outward by the same explosion, their paths frozen in time like shrapnel from a celestial grenade. The real detective work begins with shockwaves ripples in nebula gas that still propagate millennia after the initial blast. The Veil Nebula's delicate filaments aren't static. They're racing outward at nearly 1 million miles per hour, their expansion slowed only by collisions with interstellar material. By measuring their speed and composition, researchers can rewind the cosmic clock, reconstructing the energy of the original supernova. In the Vela supernova remnant, these shock fronts have even been caught in the act of triggering new star birth, their crushing pressure squeezing gas clouds until gravity takes over, a literal case of destruction paving the way for creation. What makes these echoes indispensable is their role in the grand narrative of nucleosynthesis. Every gold atom in your jewelry, every iodine molecule in your body, was forged in supernova or their even rarer cousins, neutron star mergers. The gas clouds that birthed our solar system were already peppered with these gifts from long-dead stars. The Eagle Nebula's famous pillars of creation, for instance, contained traces of europium and gadolinium elements so heavy they could only form in the extreme conditions of a collapsing stellar core. Yet decoding these signals requires instruments of staggering precision. Spectrographs like those on the Very Large Telescope can distinguish absorption lines from elements present in parts per billion, akin to detecting a single grain of salt dissolved in an Olympic swimming pool. The James Webb Space Telescope's infrared eyes peer even deeper, spotting molecules like hydrogen deuteride in nebular gas, which betray the temperature and density of ancient supernova shock fronts. Each measurement adds another piece to the puzzle, revealing how generations of stars have enriched the cosmos with the raw materials for planets and life. Perhaps the most humbling realization is that some of these echoes predate Earth itself. The iron in your blood, the calcium in your bones, their atoms were likely forged in supernova that exploded billions of years ago, their remnants scattered and recycled through multiple generations of stars before finding their way into you. When we study a nebula's chemistry, we're not just analyzing gas, we're reading a diary of cosmic alchemy written in the language of spectral lines. And in that story lies an astonishing truth. The universe doesn't just create elements, it remembers them. 31st mystery. The future evolution of star clusters, even the mightiest star clusters, are not eternal. Gravity's grip, though formidable, is no match for the relentless tides of time and the galaxy's ceaseless churn. Picture Omega Centauri, that ancient sphere of 10 million stars drifting through the Milky Way's halo. Today, it appears unchanging, a glittering fossil from the universe's youth. But over trillions of years, the subtle tug of passing gas clouds, the gravitational nudges from spiral arms, and even the occasional close encounter with another cluster will erode its structure, plucking stars away one by one like petals torn from a flower. The process is already underway. Astronomers have spotted tidal tails, streams of stars trailing behind globular clusters like cosmic breadcrumbs, marking the path of their slow disintegration. The Palomar 5 cluster, for instance, is more tail than body now, its stars stretched into a shimmering river 60,000 light-years long. Within a billion years, it will vanish entirely, its stars scattered across the galactic halo. Even tighter clusters like Messier 80 won't escape forever. Their dense cores might persist longer, but eventually the galaxy's tides will pry them apart too. Yet dissolution isn't the only fate awaiting these stellar cities. Some clusters, like those orbiting near the Milky Way's center, face a more violent end. When they plunge too close to the supermassive black hole lurking there, its gravity can rip them apart in a single catastrophic encounter. The stars that survive will be flung outward at staggering speeds, some ejected entirely from the galaxy to wander the void between galaxies as cosmic orphans. Others might be captured by the black hole's pull, doomed to spiral inward and vanish behind its event horizon. For those that avoid such dramatic ends, a slower transformation awaits. As clusters age, their brightest stars burn out first, leaving behind dimmer red dwarfs that smolder for trillions of years. Eventually, even these will fade, and the cluster's population will dwindle to stellar remnants, white dwarfs cooling into black embers, neutron stars pulsing faintly in the darkness, and black holes silently anchoring what little remains. The end result, a ghostly assembly of dark objects, so faint they'd be invisible to any distant observer. The universe's last surviving clusters won't glitter, they'll loom as shadows, their presence detectable only by the subtle warping of space-time around them. But here's the twist, even in death, star clusters shape the cosmos. Every escaping star carries with it the heavy elements forged in the cluster's heyday: carbon, oxygen, iron, seeding the galaxy with the raw materials for new stars and planets. The gas expelled from dying stars enriches the interstellar medium, ensuring future nebulae will bear the chemical fingerprints of generations past and the black holes left behind. They might one day merge, sending ripples through spacetime itself. This grand fade into darkness mirrors the universe's own trajectory. As expansion accelerates and galaxies grow ever more distant, the night sky will one day be empty of all but the faintest stellar remnants. The era of star clusters, like the era of bright nebulae and bustling galaxies, is fleeting on the scale of cosmic time. Yet their legacy persists, written in the motions of stars they once held, the planets built from their ashes, and perhaps even the life that arose from their stardust. They remind us that in the universe, even endings are creative acts, scattering the seeds for beginnings we can scarcely imagine. From the fiery birth of stars in nebulae to the ancient glow of star clusters, we've traced the universe's grand life cycle, where destruction and creation are two sides of the same cosmic coin. These celestial wonders aren't just distant spectacles, they're the architects of reality itself. Every atom in your body was forged in the heart of a dying star, scattered across space by a supernova's fury, then gathered again in a nebula's embrace to birth new worlds. The iron in your blood, the calcium in your bones, even the oxygen you breathe, all were crafted in these stellar factories, making us literal stardust given consciousness to marvel at its origins. Yet for all we've uncovered, the cosmos guards its secrets jealously. Why do some nebulae birth massive stars while others create only dwarfs? How do star clusters retain their ancient structures against galactic tides? Each answer peels back another layer, revealing deeper mysteries waiting to be solved. The James Webb Space Telescope's infrared gaze is already rewriting our understanding of stellar nurseries, while gravitational wave detectors listen for the whispers of colliding black holes in globular clusters. These tools aren't just expanding our knowledge, they're redefining what's possible, turning science fiction into scientific fact before our eyes. What makes this journey timeless is its intimacy. You don't need a telescope to connect with the cosmos, just step outside on a clear night. That faint smudge in Orion's sword, it's the glow of a stellar nursery. The twinkling haze of the Pleiades, a young star cluster, its siblings still bound by gravity's invisible threads. These aren't abstract concepts, they're our cosmic heritage, visible to anyone who pauses to look up. The universe doesn't belong to astronomers alone, it invites us all to witness its story, written in light across the vastness of space and time. So let this be an invitation, not an endpoint. The night sky is a living library, its volumes updated nightly with new discoveries and ancient light. Whether you're tracking the latest nebula imaging from NASA or simply sharing the stars with someone you love, you're participating in humanity's oldest tradition, reaching for the heavens while standing firmly on Earth. The cosmos whispers its secrets to those who listen. Keep looking up, keep questioning, and remember, every time you gaze at the stars, you're meeting the very forces that make